The expansion of the universe. So Hubble's law showed us that the velocity and distance of galaxies have a direct relationship, where the farther away a galaxy is, the faster it moves away from us. And he also showed us that all galaxies are moving away from us. So the conclusion of that is that it is not really the galaxies moving, but instead the universe is expanding. Our universe, the entire universe, remember the universe is everything, is getting bigger. Now, when we talk about the galaxies moving away from us, they aren't really moving themselves. They are being carried by space as the space expands. So if you picture something floating on water, and then you set up a wave, the wave will carry that on the water, but it's not really moving itself. It's not moving through the water, it's moving with the water. So the galaxies are moving with space, not through it. And the expansion that's taking place is only in the empty places. So within a galaxy, expansion does not take place. The galaxies don't change size. And that's because of gravity. Where there's mass, where there's lots of mass, there's no expansion. So it's where things are fairly sparsely populated, in between the galaxies, that the expansion takes place. And that expansion is what leads to Hubble's law. So here the example is raisin bread. There's lots of other examples, but raisin bread works. So you've got two raisins close together. When the bread rises, there's not much dough between the two. And so it doesn't expand much. So the distance changes just a small amount. But if you have two raisins farther apart, more dough will expand more. And so it looks like the distance has changed more. The more the distance changes, the faster they appear to move apart. So let's look at an example on a line. Let's say we have a rubber band, and I'm going to try to divide this more or less evenly. That's not even, but there you go. Let's see if I can do a little bit better there. So this is our unstretched rubber band. And now we're going to stretch it. So one in the middle, one halfway there. Now if we're going to measure from our starting point out to each of these, let's say these are a centimeter. They're not quite, but that's not too far off. So it's about 4 centimeters to the most distant one, about 3 centimeters, 2, and 1 centimeter. Now we've more or less doubled it, so let's say that's now 2 centimeters, 4, 6, centimeters, not meters, and 8 centimeters. So if we looked at the distance initially, call that distance 1, and then distance 2, and then the change. So we've got, we started off with 1, 2, 3, and 4 centimeters. We ended up with 2, 4, 6, and 8 centimeters. So that first tick mark, or galaxy, moved 1 centimeter. The second one moved 2. The third one moved 3. Fourth one moved 4. So that change is essentially our velocity. So the larger the distance, the larger the velocity. That's Hubble's law. So Hubble's law directly comes from this geometric effect that when you have more stuff expanding between you and an object, that is, it's farther away, then when it expands, it's going to change more. And that is essentially going to look like it's moving faster. So nothing is truly moving in what we're measuring here, but it's getting carried farther away faster because there's more space expanding between us and a distant galaxy. So when there's more space between us and a distant galaxy, it expands more, making the galaxy appear to move away faster. So that's how the expansion of the universe is connected to Hubble's law.